Okay, thanks everyone for coming. Today we are going to be talking about what it takes to implement the standard library. So to start off with, people who are working on the C++ standard library need to be able to turn this, which is what's known as standard ease. You do not need to read this text. You just need to be familiar with its structure. This is called standard ease, which is the text that is in the C++ standard that articulates what it is that C++ is. This in particular is the constructor for the pairs piecewise constructor. It talks about how you can take a tuple of two tuples, one of which talks about how to construct the first type, and the other one talks about how to construct the second type, and that will then give you a pair of T and U. You need to be able to turn something like this into something that your users can then go about and use. Now that could be in C++ code, or that could be in some other form of magic. We'll come back to what that magic is later on. Before we get started though, we should probably find some common ground, because standard library developers are programmers just like everyone else. And I figured that, I could probably distill what we can all agree on as being some sort of priority to three things. The first of which is correctness. The next one is some amount of good performance. And finally, good diagnostics. We may disagree on the prioritization of these three things. Hopefully put correctness at the top of the list, but I think this is a pretty non-controversial list in terms of what it is that developers do care about. And it is definitely incomplete. There are many things that we could draw on and say these are priorities. This is just a set of things that I think we can all find some common ground on. So firstly, there is correctness. And correctness comes in two flavors, the first of which is ensuring that the interface that is being described in the standard is actually doing what it is that the standard says it's doing. It would be kind of bad if the empty function returned a value other than true when a vector is empty, and a value other than false when it has elements. So that is the first form of correctness. We need to make sure that our APIs are correct. The second variety of correctness is that we should be also making sure that your programs are not misusing the standard library as much as possible. Just like the compiler checks that you are using the core language correctly, the standard library should be checking that you are using the library components correctly as well. We'll come back to this sort of stuff in a little bit. The next thing to talk about is that we care about good performance. Good performance is, a critical component of C++. We wouldn't be using it if we didn't want control over performance. And the standard library is intended to be for everyone. It's a general purpose programming language library. That means that it needs to cater to as many needs as possible. And unfortunately, that means that it is probably always going to lose out to a special purpose library, because special purpose libraries can be fine-tuned for their domain, and so they will just be able to outperform any general purpose library for that domain. However, for a general purpose library, the standard library implementations should ideally be the best of the bunch. And if they're not, then we should investigate why that's the case and see what we can do to improve it. We may not always be able to achieve that goal, but that is something that we should always be striving to do wherever possible. And then finally, the final thing that we talked about as something part of the common ground, good diagnostics. And so diagnostics, if you're not familiar with that term, are how tools communicate with the programmer. You most often find diagnostics in the form of errors and warnings and associated notes that go with the errors and warnings. And on screen, we have 3 lines of code. There is a bug in these 3 lines of code. Does anyone want to guess what that is?
No way to print S.
No way to print S, correct, yes. So in order to use std print, we need to provide a descriptor. I can't remember what it is off the top of my head, but we need to provide a way of telling print how it's going to actually print an S, and that isn't the case. Now, when you get a diagnostic, you should really feel empowered to go back to your program and fix what it is that you got wrong. You know, it may be a tough problem, it might be an easy problem, but you should feel like you know exactly what the problem is, that you can go back and fix it. Now let's check in how C++ is doing. Oh dear. Yeah, it takes 20 lines of diagnostic to get to what the problem is, and then I think it's another 30 lines to get to why it's a problem. That's not entirely encouraging. This is how I feel. So these are the goals, but how do we achieve them? Let's start out with the correctness goal, because that is the most important of the three. And so that comes to just the general engineering practices that one would encourage any developer to do. So correctness is mainly achieved through engineering practice. Unit tests, those are bread and butter for a standard library engineer. We have lots and lots of unit tests. If you look at any of the major implementations, you'll see that they have stacks of unit tests. And in fact, one of the implementations has 2 standard libraries worth of tests. I find that the best way to get unit tests, get the most out of unit tests, is to use test-driven development. And test-driven development, if you're not familiar with that kind of programming paradigm, is to write a test and then implement a wrong version of what it is you're testing, and then fix the thing once you verify that the test is actually doing something, so that way it is passing. And Phil Nash is actually the one who got me on board with TDD, because prior to that, my university had said, well, just go and write all the tests and then implement the thing. And that was kind of boring. And it wasn't until Phil really broke it down as you do it piece by piece that I understood that unit tests through test-driven development became a lot more fun and a lot less of a chore. So test-driven development is something that I do when I'm implementing things in the standard library, particularly libc++. And then as a second kind of foil to that, All Your Tests Are Terrible by Titus Winters and Hyrum Wright is a great way to learn about general purpose tests and just general practices. What can you do to make sure your tests aren't being flaky? And how can people, yourself probably, in the future, make sure that the tests are correct on inspection? These are important things to understand. And also, All Your Tests Are Terrible is just a hilarious talk and worth watching for the comedy alone. So that is unit tests in a nutshell. And we'll come back to the definition of unit tests in a moment. But before that, there is a problem with using a test framework like Catch2 for implementing the standard library. Does anyone want to guess what the problem is with using something like that to test the standard library? I see 2 hands. Anna, I think your hand went up first. Use the standard library. Yes. So that is indeed the problem. You can't really have confidence that your tests are correct when your tests depend on the thing that you are testing. And so even if everything was working okay, the very fact that that Catch2 depends on the standard library tells me, erodes my confidence in being able to trust that the unit tests are going to be correct. And so there are 2 solutions to this. The first of which is that you can implement assert, check that assert is working through just a very simple def test, and then go on your merry way. Or you can go and roll your own unit test framework. Now, libc++ and MSVC's STL both use just a simple assert. I believe libstd C++ rolls its own thing, which I think is pretty neat. but libc++, which is what we'll be focusing on in the second half of this talk, will be asserts, so we will be using asserts. I tend to find that asserts are not too fun for TDD, but that's something that we have to make do with. Okay, so that's correctness from an interface perspective. How about from a usability perspective? So on screen, we have another buggy program or snippet of a program. Does anyone want to guess what this problem is?
Out of bounds access.
Out of bounds. Oh, I even say it on screen. Well, guess someone needs more coffee. Okay, so there is an out of bounds access, yes, and this is something that is undefined. In this case, it is a bad form of undefined behavior, and that is kind of a bad thing. And unfortunately, this may or may not go noticed by the runtime. If we push something on and then popped it off and it's an int, it's probably not going to be noticed by default. And so implementations have to go a little bit out of their way to make sure that you are using vector correctly. You may ask, well, what about address sanitizer? Doesn't address sanitizer get things to work? And the answer is yes, but there's a catch to it. You can't just implement a vector-like type and have address sanitizer working straight out of the box. Address sanitizer is something that works with things that new and delete and malk and free deal with out of the box. But for something like vector, which allocates a buffer and then grows until it reaches the end of that buffer, you can't get that kind of input from address sanitizer. You need to teach address sanitizer that this is where the vector stops having valid data, and anything in this section of the buffer is actually not allowed to be accessed. And so there's a fair bit of machinery that goes into implementing vector just to teach it how to talk with address sanitizer, and how address sanitizer can give you a diagnostic like this and then crash your program, so that way you know you're doing an invalid memory access. With libc++ and MSVC's STL, just build with address sanitizer turned on for your entire program, and this will work straight out of the box. libstd C++ requires you to enable a macro as well, just to make sure that you are opting into saying, hey, I know that if not everything is built with the fsanitize address enabled, then I may get false positives, and the false positives are never fun. So that is how we get address sanitizer and things like vector to coordinate together. Is there anyone in the room who isn't familiar with address sanitizer, by the way? Okay, so address sanitizer is a way of making sure that you use your memory accesses correctly. It checks that you are not accessing things out of bounds. It also checks that you are freeing any memory that you've allocated manually to ensure that you don't have any memory leaks. Does that give a rough idea of what it is? Cool. Okay, so that's great. Address sanitizer helps us with things like vector and memory-related things, provided we know how to talk with it. But it doesn't capture a problem like dereferencing an empty optional. That's just not something that address sanitizer knows how to help with. And you could say, well, aren't there other sanitizers that might be able to catch this? And that may be the case. I'm not 100% sure if there are. But let's pretend for a second that there weren't any that were easily available. Because there are some sanitizers that do require a few hurdles to get over. Since those aren't going to be as widely available, the way in which we would get something like dereferencing an empty optional to be detected is to fall back to design by contract and put in some sort of precondition that will then abort the program with a helpful diagnostic. And this is an example of how libc++ does it by asserting when has value is false, and then the program just crashes. In order to turn that on, you would enable a flag that talks about hardening mode for libc++, and for libstd++, I think it's called assert mode. When the slides are available, you'll be able to click on the links that are at the bottom of this slide. That'll take you to how to get this sort of stuff on. And libc++'s hardening mode is actually designed to run in production. It's very lightweight up until you get to the debug mode, I believe. The documentation makes it very clear what kind of performance impacts you can expect. But of course, when you turn these things on, you do need to benchmark. Now, let's go on to a new problem, because there are many problems in this correctness section. Is this code okay? Does anyone see a problem with this code? I see a hand.
Like the distribution hasn't given like a character.
So the question is, sorry, the response is it's been given sign char.
Yeah, it's that like operated into the past.
So I didn't catch that.
Shouldn't aim to be passed instead of like character.
Okay, so the question is, should that be an int or something? And we'll come back to that in 30 seconds. But yes, you have homed in on the right on the right point. So this was taken from a test framework in a very large code base, and it was working for years, and then it randomly broke one day. And when I say randomly, what I mean is that from the perspective of the users, it just suddenly stopped working. Things just didn't compile, and they were pretty confused about this. And it turns out that it was because they had a uniform int distribution over sign char. Now, sign char is the canonical way to say that you want an integer of size 1, but the problem is that the standard says that anything that is out of the realm of a short through a long integer, then the program is undefined. So that means that if you have an integer, so if you have a 1-byte integer, or you have a 128-bit integer that is offered as an extension, as Clang and GCC both offer, then those are undefined. It also means that C's bitint, which Clang supports in C++, is also undefined. And so the implementation at some point had realized that sign char was being supported, and they didn't have any tests for this. And so they had concerns about not only its correctness, but about a couple of other things. And so they disabled support for it. And this was an interesting thing, because that doesn't mean, just because the standard says that it's undefined, doesn't mean that it's automatically wrong. When we think about undefined behavior, typically we jump to the conclusion that undefined behavior means badness, that the program is wrong, and like we need to get rid of the undefined behavior. But if we look at the definition of undefined behavior, we see that it says that it's behavior for which this document imposes no requirements. It doesn't say anything else. It just says those few words. And if you read on a little bit later on, it talks a little bit about program execution, but that doesn't really say anything about you cannot have undefined behavior in your program. If you read through the full description of undefined behavior, then it talks about all the ways in which it can manifest. Again, don't have to read that giant block of text. Really, what undefined behavior means is that the implementation decides if the code is valid. And it can also mean that it's at their leisure, or that the implementation can add an extension if they document it properly. These are all things that can happen. And so what ended up happening with that sign char story is that the implementation added an extension to support sign char, so that way people could actually continue to use single byte integers with their random int distributions. The only exception to this is that core constant expressions cannot be considered an extension when it comes to undefined behavior, because the standard explicitly says that those are to be ill-formed. That means you get a program diagnostic. Now, a lot of undefined behavior is still badness, such as dereferencing a null pointer or accessing things beyond the bounds of an array. But there are times when it makes sense to add an extension. Sometimes the standard just doesn't have a good way of saying, look, this could be an error or this could be a valid use, so we'll make it undefined. And where I'm going with this is really that we need to plan for Hyrum's law. Is there anyone in the room who is familiar with Hyrum's law? Okay, that's a fair few hands. Can I get the inversion of that, please? Who's not familiar with Hyrum's law? Okay, about half the room. That's a good split. So Hyrum's law is an observation made by a former colleague of mine, Hyrum Wright, who observed after working on a lot of software that with a sufficient number of users over an API, it does not matter what you promise in the contract, all observable behaviors of your system will be depended on by somebody. And what this means is, in phrase another way, is that if someone can touch something, then it will be touched. Doesn't matter if you put up a big sign that says "Don't touch," or you shoo a 3-year-old away saying "Caution." This you wouldn't say caution to a 3-year-old. Go away. This oven is hot. Eventually, that 3-year-old is going to touch the oven and learn the hard way what a hot oven is like. So that is Hyrum's law in a nutshell. Does anyone have any concerns about that definition? I don't see any concerns. Cool. So it is an inevitable property of software engineering. Hyrum's law will eventually be reached. All we can do is plan for when it does happen, and then respond to it once we've actually realized it. We can get in front of it. We can never actually stop it from happening at some point. There are a few different responses that we can have. So the first one is that we say, look, we're not going to make this change. We broke someone, and that was unacceptable. We'll revert this thing and never ever fix it. The next one is that we will do a temporary rollback. We'll stop the pain for a little while, but you are on notice. You are going to have to fix it, and you're going to have to do it before a certain date. The next one is to do a tiered release. And that basically means that you have to opt into the feature in the next release, followed by it being opt out the release after that, and then it's removed in the third release. Now, there doesn't have to be releases 1, 2, and 3. It could be over a broad period of time, but the idea is that you slowly transition your users. The next one is prioritizing a forward fix, so that way the people who are broken are not hurt for that longer period of time. And then finally, you have the exact opposite of where we started, which is there was nothing to fix. You were using things wrong, and we're not going to fix anything here. Or there are not enough users that are being impacted. Usually, it's not. Not usually. Always, it is never a point of malice. It's a case of, look, there is not enough evidence that this is something that we should be prioritizing a fix for at all. I like the middle one because it is the way that we can have our cake and eat it too. It means that the people who want to have the new feature as quickly as possible get it, and the people who are not yet ready to move on to the new feature are not going to be broken immediately. They have some time to respond to it, and then it gets us progressively over the speed hump. Now, I did mention that we can get in front of it. And it says here that we can prevent it. There is a way that we can prevent it, but it's costly. So we need to be forever vigilant. The first way to do that is to simulate user input using fuzzing. Does anyone want a refresher on what fuzzing is? Okay, so okay, cool. So fuzzing is a program that runs indefinitely, and it just generates random input. And that random input is then fed to some part of your library, and then it will respond to that. And if it's expected behavior, then it should just continue on as if the function was never run. But if it produces something that's unexpected, the program should crash. And then you respond to the crash, you make a new unit test, you fix it, and then you go and rerun the fuzzer, and it will just continue to do that. So that is the first way. It's a very important part of development. The next way is to do integration tests. Now, I mentioned unit tests a fair bit back, and those are good at checking that things work in isolation, but they don't check that things work as a whole. Sure, vector might work on its own in the unit test, but that doesn't mean that people are using it in some weird way in their own programs. That's not something that we can really tell unless we go and check how things are working in the wild using vector as people actually use it. And the standard library is a pretty unique library in this regard because it's used by everyone. And so we can just go and build the world. We can build an entire operating system in all of its packages, and that will give us some signal. FreeBSD and Gentoo are good for libc++. Debian and Fedora and Gentoo are good for libstd C++. And MSVC will take care. The release team will take care of doing their one for you. But if you want to make a change to libc++, then you would be able to go and build FreeBSD and see if anything breaks. And then if it doesn't, that's great. You have a lot of confidence. The problem is that this is incredibly slow. Building an operating system and all its packages isn't something that we would want to put in our CI on a commit by commit basis. It's something that you'd want to have run at best nightly, maybe even weekly. It's something you have to batch. So this will catch as many Hyrum bugs as early as possible, because the idea is to catch things early, notify people that there is going to be a change, and then get them to fix things before the release happens. Okay, so we've talked about correctness for a bit. Let's change gears and talk about performance now. So performance is secondary to correctness, but it's still critically important because why else would we be using C++ as opposed to a different language? Performance comes in two flavors. The first of which is speed. The second is size. We're focusing solely on speed today. Okay, so the most important thing is that we're not concerning ourselves with big O notation here. We're going to assume the algorithm is already optimized from a mathematical perspective, and we are trying to milk out as much as we can from something that is already supposedly optimal. We just want this thing to go as fast as it possibly can. And in order to do that, you need to know what your use cases are. You can't make decisions about performance unless you know your use cases. So profilers are going to be critically important here, and you're going to need to be doing benchmarking on your old version of the library versus your new version of the library to ensure the change is actually worthwhile. It's not just change for change's sake. And then you need to also ensure that all the relevant optimizations are enabled. There's no point in doing benchmarking if you don't have all of the optimizations on. So let's take a look at std_vector, because std_vector is a pretty common type, and it's also something that everyone should have a good working mental model of as well. So something that you might learn about in C++ 101 class is that a vector is something that has a pointer to some data, and it has a size and it has a capacity. And so the size indicates how many elements are currently in the vector, and the capacity indicates how much memory is available before we have to reallocate. And unfortunately, this is not how you implement std_vector. Std vector is a little bit more complicated because it allows you to have control over how memory is allocated. So we need to have this thing called an allocator, and that will not only handle where the memory is obtained from, but also do things like ensuring that you construct your types in the correct way according to how the allocator wants things to be constructed. So this also, because you are having to do manual construction, implies that you have manual destruction. And so these are things that Vector needs to take into consideration. And if you go and look at the major implementations, then you will notice that it's not implemented using a size and a capacity, but rather as using 3 pointers. I like to call this particular model the 3 pointers in a trench coat model. And you might think that because all 3 implementations are doing it this way, there's a pretty good reason for it. And I think historically there may have been, but benchmarking has shown that, in fact, the previous implementation with size and capacity as integers may actually be significantly faster. Research is still necessary to draw a conclusion that makes this general purpose. But so far, the data that we've obtained is pointing in that direction quite encouragingly. That if we change from using 3 pointers to a pointer and 2 size types, then we'll end up with a vector that performs a fair bit better than the current one. So keep an eye out for that in release notes in the future. I see a hand.
Yeah. So like where is the performance benchmark on the three that you make?
So the question is, where is the performance coming from? So originally, the full answer is a lot more research is necessary in order to get an answer for this. The simple answer is that based on the usage patterns that we have observed, we're doing additional arithmetic to get the size out of the vector, and that is happening frequently enough that it is they're calling size and doing that additional arithmetic, because with the 3 pointer model, you have to subtract size from begin in order to end from begin in order to get the size. If you just have an integer, you can just return that directly. And unfortunately, I can't give much more information because that's as far as we know at the moment. There is still a fair bit of research that needs to go into this. But when this research was being done, something that came up was that things were going a little bit slowly on my machine versus one of my colleagues' machines, and that's when I learned that turning on profile guided optimization is a critical part of benchmarking. Now, profile guided optimization is an optimization where you compile the program with some instrumentation, and then you run the program on some data, and then it will generate a profile that you can then feed back to the optimizer to produce a better program based on how users are actually using your program. And that ended up having a significant impact on the data that we got. And the crux of this is that unless you have benchmarked your code, you really shouldn't be talking about performance. Benchmarking is the critical part of this. A lot of the things that we learnt and are still learning is only possible through benchmarks. There are 2 flavors of benchmarks, the first of which is micro benchmarks. These are like unit tests. They test things in isolation, and they don't give you a very strong signal. Macro benchmarks, on the other hand, are whole program sorts of benchmarks and give you much stronger signal. They are influenced by optimizations quite significantly. Now, I believe we are 30 minutes in. So you're probably wondering at this point, what does any of this have to do with the standard library? You've just been giving general software engineering tips here. And the answer is really everything. This is our bread and butter. We don't know that things are correct unless we do all the regular correctness tests, and we don't know that things are fast unless we do all the performance tests. When I talk with people online, I do a fair bit of popularizing LLVM and trying to get people to contribute to libc++ or Clang. People give me the impression that they think that contributing to the standard library is like summiting Mount Everest. And that's an impression. I think it's more like trying to summit Mount Kosciuszko, which is the tallest mountain on mainland Australia. It's really more of a big hill. You can even see a path that you can walk up. That's this, I've forgotten what it's called, but I think it's the Kosciuszko Trail. And that is, I think, a really nice image, because the standard is kind of like that path. It's already done all the hard work. You were just going ahead and implementing what it's telling you to implement. It's a challenge. You do need to be somewhat physically able to get to the top of Everest, but it's something that that whole families do on an annual basis. And so I do think that that it's a much easier challenge than people make it out to be. The real challenges that are like Everest are in the safety critical domains, where people's lives are at stake. Medical sorts of things are more in the Everest domain. Standard library stuff, yes, it's challenging, but everyone in this room is more than capable of trying it. Having said that, it is important to understand what it is you're getting yourself into, because it's not all sunshine and rainbows. So again, we're about half an hour in, and I haven't defined what the standard library is. If you ask someone who is just starting out with C++, or doesn't really think about things from a language layer perspective, they may tell you that the standard library is just the set of headers that come with the compiler. Like that's a pretty good definition of it. And then if you talk with someone who sits on the committee, or you talk with someone who likes to read the standard for fun, then they may tell you it's the body of text that spans the library clause through the thread clause. And that's also a valid definition of what the standard library is. I think the one thing they can agree on is that it's in namespace std. And or libc, because libc is a part of the standard library too. So the answers come in a spectrum. Don't really care about anything in the middle, because it all just boils down to this it's in std. And so, we should probably talk about, well, what does that mean? What is the standard? What are the things that we can agree on, and how do we get this information? How do we go about, working out what it is that we're actually trying to implement? And so for that, we need to understand that you don't use CPP reference. Now, reading the audience, guessing this is how you're feeling right now? So it's okay. You can still use CPP reference for your regular programming on a day-to-day basis. I use CPP reference to build these slides. The problem is that for building the standard library, CPP reference has a set of things that it omits, either deliberately or by accident. It's an interpretation of the standard. It's designed to communicate what the standard says to someone who doesn't want to read the standard, or shouldn't read the standard because it's not their job to read it. So sometimes those omissions are deliberate. Sometimes it's worded in such a way that just things that aren't relevant are dropped off. Sometimes, because it's a wiki, people make mistakes. And so if you implement something by reading CPP reference, it's like taking a photocopy of a photocopy. You've interpreted someone's interpretation of the standard. And let's run through an exercise, because that is the best way to understand this. So here's the CPP reference definition of the pairs tuple-wise constructor. Sorry, the pair-wise constructor for std pair, piecewise constructor for std pair. We'll get it right one time. And so what we have is the CPP reference definition for that. As it goes through, gives a description that is fairly interesting and mostly correct. In fact, this is something that I would say a user should be reading about this. The problem is that in the standard ease, it has this mandates clause. And that is something that the CPP reference definition doesn't mention at all. And that is a problem. Let's explore what this mandates means, and then we'll come back to why it's a problem. So the standard has certain words of power. A word of power is something that so we have a verb that then has a description that the standard has outlined. This is what this word means. It's not the English definition of it. We're giving it a very strong definition here. And mandates is one of these words. Another one is constraints, and then we have a few others. So with mandates, it says that if the conditions in the mandates paragraph are not met, then the program is ill-formed. That means we don't get a valid program. The compiler issues us a diagnostic, and that's it. There's another one called constraints. And constraints say that this function doesn't participate in overload resolution. And you can think of that one like a, sorry, I didn't explain the second paragraph. Mandates can be done using a static assert. Constraints can be done using a requires clause. And so because the standard says mandates and CPP reference doesn't, that means that based on which document you've read, you may implement this piecewise constructor slightly differently. And that is a problem because certain programs are required to compile even if they produce the wrong result. And so this is one such example where this returns false. So this should return false, but it returns true based on the wording from the standard. And so unfortunately, if you use constraints here, so if you use a requires clause here instead of a static assert, this will return false and some programs may break. So we need to follow these things very strictly. Now, you may be saying to me, Christopher, this is an esoteric constructor. It's probably just not had a lot of traffic. And so, just go and add the mandates bit and be on your way. It's not like this is happening to vector. Well, sorry, it is. It's also happening in a very common constructor for vector as well. And so this is a very good definition. Again, I'm very happy with what is on screen in CPP reference. The problem is that the standard ease outlines a precondition. And this precondition is something that you might miss out on if you are not reading the standard ease, and that can lead to problems because these things are being omitted. And just like I was saying that simply depending on the standard library is enough of a disqualifier for confidence when it comes to testing the standard library and a test framework. These omissions are enough of a disqualifier for confidence in trusting CPP reference for implementing the standard. So it's not that you can't use CPP reference ever. Please continue to use it. Don't go and consult the standard unless you need to. But when you're implementing C++ or you're reviewing someone's contributions to implementing C++, it is very important to go and read the standard ease, not CPP reference. Don't thumb CPP reference, just go and check the standard. The working paper is available online for you to go and check. And there is even now a search engine that allows you to index things. So it allows you to find things based on indexing. But please do continue to use CPP reference when you're writing user programs. They're still very important. Okay, so we've covered that. We should also cover what the C++ implementation is, because that is a word that is thrown around by the standard quite often. And so typically when people think about this, the C++ implementation, they think about it as a compiler that produces a binary and there's some runtime support library. And that's kind of what we have. But if we think about it a little bit more, we realize that there's also a linker. And the linker is an important step that we shouldn't omit because it plays a vital role in building a program. How often have people run into linker errors that have, yeah. No, understanding the presence of the linker and that it happens after the compiler is very important. But that is not the only thing that we need to think about, because now we need to break down what is this runtime support box. And it turns out that, there's some compiler runtime support, there's a C++ standard library, there's a C standard library, and there's exception handling. And those are the four main ones. There are many others, but these are the four ones that we will concern ourselves with, because those are the core ones. Everything else is sort of peripheral. And we should note that the compiler has a special relationship with the C++ standard library in particular. We'll come back to that in a little bit. After we think about the runtime support, we need to note that there are many processes, and the operating system, if there is one, houses all of that. These things need to live somewhere. Now, I'm going to gloss over things like containers, virtual machines, and freestanding. If you're thinking about freestanding programs, I've got a slide for that in the next one. Just pretend this one didn't happen. And that next slide is hardware, because things need to happen on some hardware. It's not something that that just happens in some sort of ethereal place. No, this stuff actually does happen on real hardware. And so the important thing here to realize is that all of this forms an ecosystem. The implementation isn't just the compiler and the standard library, it's everything put together. The hardware has an inextricable relationship with the compiler has an inextricable relationship with the runtime support libraries, the operating system is also involved in this, and your program is too. Everything forms the implementation. And that's a very important part of understanding what it takes to implement the standard library, because these are things that you will need to be considering when you're implementing certain parts of the standard library. And that's why I like to think of standard library implementers as a special kind of compiler developer. This is not a universally agreed upon opinion, but I see the standard library as an extension of the compiler, because the compiler is the primary piece that does the implementation for us. We break things up into separate projects, like we have Clang and libc++, we have GCC, libstd++, we have a variety of operating systems and hardware, but really the two main characters in this are the compiler and the standard library. And when we think of them as being the standard library being an extension of the compiler, a lot of things just fall into place. For example, it's not possible to implement the standard library in C++ purely. There's some things that we can't do. For example, we can't implement is trivially copyable because in just code, because the compiler is the thing that knows whether or not something is trivially copyable. There's no way to write C++ and detect if something is trivially copyable without using that query is trivially copyable. Then there are some things that direct input from the compiler can be optimal. It's not required, but it can make things faster to build, it can give better diagnostics, it can lead to better code generation. There are a variety of reasons why putting things in the compiler can lead to better programs. Now, there are some things that Clang supports, and there are some things that I'd like to see Clang support, but haven't quite gotten around to seeing them implemented yet. But if you're thinking, well, why don't we just put everything in the compiler then? The answer is no, we shouldn't be doing that, because most things still belong in regular C++. Putting things in the compiler is extremely difficult work, and it's not really worth the effort to put things in the compiler unless there is a noticeable and detectable, unless there is a detectable benefit that we can use to our advantage. So that's why we would not put things in. Now let's talk about what that actually means in a little bit more detail. So remember that we want good diagnostics. Does everyone remember this little program from the start? Okay, let's just check in with how things were. Yeah, not great. Slightly better, because in this particular implementation, the diagnostic is all the way at the top, but it's still really kind of this sort of thing. And having said that, I would take this kind of a diagnostic. This is a third implementation just to round things out. I put one from each implementation. I would take this diagnostic over this diagnostic any day, because if we get this diagnostic, it means that it wasn't, it didn't make the release. And so putting something in the compiler is good. It's noble. It's great because users get better diagnostics, they get better compile times, but that extra work does mean that you're spending a lot more time on this. And if that means that it slips into 1 or 2 releases down the line, that means users aren't actually going to be able to benefit from that. And so we should always put things in the standard library as C++ first, and then if we can, and then iterate on that to get the best possible thing slightly later on, and always look to the horizon to see what we can offer our users over time. Does anyone have any concerns with that? Question? 2 questions or concerns?
That it says we can iterate to replace an ABI tool.
Mm-hmm.
We have to change like the layout of the client data.
So the point was that if there's an ABI, there's an ABI issue, you have to change a class, you can't do it. In what particular way do you mean?
So we can't drag like a new positional base of language class.
Mm-hmm.
It's an ABI break, right?
Sure. Yes. So by putting the interface into Clang, we wouldn't see an ABI issue. Are you talking about moving things into the compiler, or are you talking about just generally trying to iterate on things?
We are trying to create some things, but that's why it's time and break it to stop.
Okay, I see where you're going with this now. Yes. Okay. So right, we can't just we do need to provide a high quality thing ahead of time. But where I'm going with this is putting something in the compiler as the first at the first stop, because something should be implemented in the compiler isn't necessarily the right thing to do, because it means it could miss a release. And by moving something from a source implementation to the compiler, that is not going to impact ABI in this regard. Is that?
No, I was not prepared for that one.
Oh, okay.
So you can put the implementation into the standard library first. And
yep.
Trace on it, like.
Right. With respect to getting things into the compiler.
Yeah, just that.
Right. Yes. You are absolutely correct in you should when things are implemented in source, get the best possible thing for source as quickly as possible. And if there are ABI concerns, which we will talk about in the second half of this, about how to avoid that sort of problem. Because yes, you're absolutely on point with ABI concerns. Would you mind if we took your point after? Oh, cool. Okay, great. Okay, so can we do better with this print problem? And so if we look at what's on screen right now, we have printf, and printf provides us with a warning if it doesn't know how to print something. The reason for this is because printf is an entirely runtime thing. C has no way of detecting these sorts of problems. And so if the compiler doesn't step in, then we end up with undefined behavior. And this sort of undefined behavior is just, it's not bad, it's just surprising. Sometimes it can be annoying. Printf does some interesting things when it doesn't know what to do with the input it's gotten. But if printf can do this, why not print? So this is a diagnostic that we could potentially put into Clang to produce something that's a little bit nicer. I would actually like to see it go a little bit further and provide us with a description of what we can do to get started. The reason for that is because I don't ever remember how to implement the thing for std format, and just having a bit of starter code there would kind of be nice. There are a few different ideas about this. I've typically leaned on the idea if we should be putting this into the compiler directly. There are some other folks who have said, well, if we get the abstractions for the standard library to be able to communicate with the compiler, then perhaps we could get everything that we wanted out of just the regular code. And that is something that I'm very open to exploring, especially now that it is likely that we will have compile time exceptions in a future standard. Now, I'm not sure when that will be, but I do know that it is going, that particular effort is going through wording review in the committee at the moment. So the takeaway from this is that compiler extensions are good for the compiler to use on your behalf. I don't really hold an opinion on whether or not you use extensions in your own programs. If you want to, that is your business. If it makes your program better and makes your life easier, have at it. Like that is great. But for the standard library, using compiler extensions leads to a better experience for users. There is no reason that the standard library shouldn't be using these things, because an implementation is not something that is portable. It is the thing that you are getting to get your program to work. And that pretty much brings us to the end of the session. To recap, the compiler and the runtime are inextricably linked, and that's good. We should always think of these two things as two peas in a pod. Our engineering practices are the same as yours. That is something that I really would like you to take away as well. And so really, what it takes to implement the standard library is a fair bit of tenacity. It's something that takes a lot of hard work to get to, but it's not something that's out of reach for any C++ engineer. It just really takes a fair amount of your time and getting a bit of domain knowledge. And so if you've sort of gotten to the end of this session and gone, well, okay, I think maybe I do have what it takes to be a standard library engineer, but you haven't really talked about how to do any of that. Does anyone feel that way sort of right now? A couple of hands, cool. Would have been kind of embarrassing if there were no hands. Okay, so if you're coming back for part 2, then we will talk about what you can do to implement things in libc++ specifically. We'll do a live demonstration of implementing a feature in libc++, and we probably won't get through all of it, but we will get through a fair bit of it and see what the process is like. So with that, I'd like to thank you for your time. This has been what it takes to implement the standard library.